the sodium comes rushing in. And the cell gets more and more positive. So this is a diagram showing you the cell membrane with the channels opening. Here's a potassium channel. This one's open, because remember I said some potassium channels are ungated. This one's closed, because some are gated, but it doesn't much matter because the forces want two different things. But the sodium gates are all closed at rest. Then, when action potential happens, when we reach threshold, they open, and sodium comes pouring into the cell. This graph is showing you the change in voltage of the neuron, okay? So this is the voltage, and this is time, over time. So here's how the voltage is changing over time. So we start out at rest at negative 70 millivolts, bless you. We start at rest, negative 70 millivolts. Some of the sodium gates start to open, sodium comes in, gets a little more positive, gets a little more positive, gets a little more positive, till we reach threshold, about negative 55. Then all the gates open, boom, sodium comes rushing in. And as sodium comes rushing in, the cell gets more and more positive, because more and more positive stuff is coming in. And in fact, it goes past 0, and all the way up to like positive 30, positive 40, depending on the cell. It's really positive in there. That process is called depolarization. Because when we're at negative 70, we're polarized. We're very negative. We're polarized. And so going up towards 0 is the depolarization. When we reach the peak of action potential, at the peak of action potential, right here, the peak of action potential, around 30 to 40 millivolts, at the peak of action potential, sodium gates close. At the peak of action potential, sodium gates close. When action potential is at its peak, sodium gates, also called sodium channels, close. I said that like a bunch of times, so possibly could be on the test? Possibly? Okay, just saying. And in the same way that the voltage of negative 55 is where those sodium gates open, the voltage of positive 30 is where those sodium gates close. They have a magical voltage for opening and a magical voltage for closing. It's not magical. You can go into the mechanics of it and look it up online if you want to. It's not at all magical, but it's much more complicated. Do you know that you're just getting the basics in this class? It's actually much more complex than this. Oh, okay. So, sodium gates close. Right after that, the potassium gates that were closed, the ones that were closed, open. And now, there's a lot of potassium inside the cell still, but now it's positive inside the cell. And so now both electrostatic pressure and diffusion want potassium to get out. So potassium starts to pour out of the cell. After the peak of action potential, potassium's pouring out, and as this positive ion pours out of the cell, it becomes more and more negative. That's called repolarization. Yes?
What's the difference between resting and gradient potential?
Between resting and graded potential?
Yeah.
I'm right about to talk about that. You're right where I need you. We'll get there in just a second. Great question. Okay. So we're coming back down, repolarization, potassium's going out, but this is when our little friend, the sodium-potassium pump, starts working. Because what the sodium-potassium pump wants is to put everything back to rest. It wants to, now all this potassium has left the cell, and it wants it to come back in, and all the sodium came into the cell, and it wants it to get back out. So the sodium-potassium pump is like an active little pump that pumps 3 sodiums out for every 2 potassiums it brings in. So that also makes the cell more negative. Yes?
So at hyperpolarization, that's when the sodium potassium pump starts?
Yes, right about there. So that part, as you so correctly pointed out, is called hyperpolarization. Because the cell actually, for a very brief period of time, gets so negative that it goes below -70, hyperpolarized. They also call that period of time the refractory period. And the reason it's called the refractory period is because it takes more stimulation to push it back up to action potential. If it's more negative, it takes more stimulation to come out of action potential. And that's one of the ways that your brain knows how strong a stimulus is. Because if we come out of the refractory period very quickly, it must be a strong stimulus, like a bright light or a loud sound or a stinky smell. But if the refractory period lasts longer, well, it must not be as strong of a stimulus. It must be a dim light or a soft sound or just a little waft of a smell, right? And so that period of time is actually really important for our brains to be able to tell, not just that a stimulus is present, because action potentials are all or none. We either saw the stimulus or we didn't. But because of that refractory period, we can also tell how strong it is. This whole action potential, from beginning to end, is taking place, like it says here, in about 7 milliseconds. 4 to 7 milliseconds? Milliseconds. Thousandths of a second. So if okay, this guy's called the Poke, and my daughter, who's 4, named him the Poke, and he gets taken away more than any other toy. Okay. So if I take the Poke, and I poke my finger with the Poke, I have dendrites in my finger that are receiving that information, and then sending the information along the axon through an action potential into my spinal column, where there are other nerves that are then carrying that information up to my brain that tells me the Poke is poking me. The reason that that happens almost instantaneously is because of how fast an action potential happens. This happens extremely quickly. The part of the cell, the part of the neuron that's monitoring the voltage of the cell, is called the axon hillock. It's this part right here. And the axon hillock works something like the thermometer in a room. Okay. The thermometer in this room is monitoring the temperature of this room. And when it reaches, I don't know what it's set for, 75 degrees, the air conditioner will kick on. The axon hillock is monitoring the voltage of the cell. And when it reaches -55, an action potential will happen. It will turn on an action potential. And the way it does that is because there are a whole bunch of voltage-gated sodium channels here that fly open when the cell reaches -55. When the cell reaches action potential, or when the cell reaches threshold, all the sodium gates that are along here that have been closed open. Sodium comes rushing into the cell, and it creates an electrical charge right here. That electrical charge then jumps across the myelin, and on and on and on, jumps down the length of the axon until it reaches the end feet. If the cell receives some stimulation, but not enough to push it to action potential, we call that a graded potential. A graded potential can actually occur in both directions. So you can have a graded potential that pushes you a little towards action potential, and another one that pushes you a little bit away. I'll talk more about that and how that works in a little bit. But right now we're talking about the ones that push you towards action potential. So it's getting more and more positive. It's -70, some sodium gates open right here at this part of the dendrite. Okay, it starts to get positive. The sodium gate opens up right here. Okay, it gets a little more positive. Sodium gate opens up right here. It's a little more positive. Axon hillock is like, okay, I'm monitoring all of you. Are we at -55 yet? Yes. Sodium gates open. Electrical impulse jumps. Sodium gates open. Electrical impulse jumps. Sodium gates open. Electrical impulse jumps. Sodium gates open. And on and on and on The electrical impulse jumps across the myelin, along down the axon, until it reaches the end feed. Yes, we'll talk about it more about it in just a second. You're right there. Okay. So, now I have a little video where a guy with a very cute accent says the exact same thing I just said. Okay. Yes. Three sodiums out, 2 potassiums in.
Hello and welcome to Interactive Biology TV, where we're making biology fun. My name is Leslie Samuel. This is episode 13, where we're going to be talking about the action potential. I'm basically going to be giving you a review of the concepts that we've been talking about up to this point when it comes to the action potential. Over here, we have our neuron. And the part of the neuron that we are going to be focusing on is the axon. So that's this region here, starts here, and it goes to about there. Now what I'm going to do is I'm going to take a section of the neuron. So let's say I'm going to take this part here, and I am going to draw it down here. So here we have the axon. This is inside the axon, and this is outside the axon. Now, if you remember from a previous episode, outside the axon we have a lot of sodium ions. So I'm going to draw sodium ions here, and they are all outside the cell. Now let's look over here. Here we have a stimulus that's happening, and you can see there's a first stimulus that does not reach threshold, so nothing happens. Another stimulus comes. It does not reach threshold, so we still do not get an action potential. If we have a stimulus that's strong enough, and I'm going to draw another stimulus in here. So let's say we have a stimulus that's that big. That's going to reach the threshold and cause an action potential. When that happens, voltage-gated sodium channels are going to open, and that's going to cause sodium to rush into the cell. Of course, that's going to start at the axon hillock. Sodium is going to rush in, making the membrane potential even more positive, causing more channels to open, more sodium to rush in, more sodium to rush in along the axon. What is that going to do to the membrane potential? You can see right here, this is where we get depolarization. The membrane potential goes up and up and up and up, and it's trying to reach the Darwin equilibrium for sodium ions. And that equilibrium potential is somewhere around 58 millivolts. So sodium is rushing in because of the driving force causing sodium to go in. Sodium wants the membrane potential to go up to its Darwin equilibrium, and that is around 58 millivolts. At this point, voltage-gated potassium channels have enough voltage in order for them to open. So I'm going to erase all of this now, and we're going to take a look at the axon again. I'm going to draw it here in blue. And inside the cell, we have a bunch of potassium ions. Now we have such a positive charge on the inside that potassium ions want to leave because positive repels positive. When voltage-gated potassium channels open, potassium can now leave the cell. So we have a lot of positive leaving the cell. And what that is going to do is cause repolarization where the membrane potential is going down. Just like with sodium, potassium wants to reach its equilibrium potential, which is somewhere around negative 93 millivolts. And that is why the membrane potential is going down as it's leaving, because potassium wants the membrane potential to be at negative 93 millivolts. That is where it is most comfortable. Considering that the resting membrane potential is around negative 70, the membrane potential goes significantly lower than that negative 70, and this phase we call hyperpolarization. All along this process, we have the sodium-potassium pumps that are pumping sodium out of the cell, 3 sodium ions out, and 2 potassium ions back in. And that's going to cause the membrane potential to eventually reach back to its resting state. This is the entire action potential, looking at depolarization, repolarization, hyperpolarization, and in getting back to the resting state. I hope that